Okay, this video is going to go over RLC circuit models and how to get them. So to model RLC circuits, we're going to make use of Kirchhoff's laws. So Kirchhoff's current law states that the sum of currents at a node must be zero. So for example, if we have this node here, this point where a bunch of wires interconnect, we have one current I1 coming in and then I2 and I3 coming out. What this law says is that I1 minus I2 minus I3 has to be equal to zero because that node there can't store any energy. So all these have to be equal to zero. And then for Kirchhoff's voltage law, this says that the sum of the voltages around a closed loop must be zero. So let's say we have a circuit with a voltage source. We have four different elements here, our capacitor, our resistance, actually two resistances and an inductance. And we're going to assign a current I that's flowing around here in the clockwise direction. So what this law says is that the sum of all these voltages based off of the sign convention here has to equal zero. So in this case, we go around the loop looking at all the voltages. VC will be positive, VR1 will be positive, VL1 will be positive, and then the last two elements, because their sign convention is the opposite as the others with respect to the current, those will be negative. So we have VC minus VR plus VR1 plus VL minus VR2 minus Vs has to be equal to zero in this case. And that's what this law says. So the steps to model RLC circuits. Well, step number one is going to be assign coordinates and state variables. So each independent capacitor gets assigned a charge or a voltage for a state. Each independent inductor gets assigned a current for a state. And then we're going to assign our plus or minus sign convention for each element's voltage. And similarly, for each branch, we're going to assign a current and a current convention for that branch, so the direction of the current. And then the second thing that we do is we're going to use the following tools to write the first set version of these equations. So we have Kirchhoff's voltage law. We have elements in series have the same current. Elements in parallel have the same voltage. We can use both of those. And then our voltage relationships for elements, we also want to use those, like V equals to IR, etc., things like that. For step number three, for any capacitors, we're going to determine the rate of charge of the state, which is going to be equal to a current that's flowing through that capacitor. And then for the final step, we're going to use Kirchhoff's voltage law and simplify to get a state space model. And just as a note, there are plenty of other ways to go about this. This doesn't need to be your only set of steps, but this is a methodology that I like to use to generate RLC circuit models. And that's going to cover RLC circuit models.